Hi everyone, this is Andy Robertshaw. I've got a video for you today on which Pythagorean triples can be generated by Euclid's formula. Might sound a bit bamboozling at first, but I will explain just what I mean by that. So, basically, I watched a video given by a chap called Simon Terrington, who's got his Maths with Simon channel. One of the interesting things he showed on his videos was Euclid's formula for generating Pythagorean triples. So hopefully we all know that Pythagoras' theorem is the sums of the squares of the two shorter sides of a right angle triangle equals the square of the longest side, the hypotenuse. So I've got a diagram here. A and B are my shorter sides, C is my longest side, a squared plus b squared equals c squared. And what Euclid's formula says is for two numbers m and n, both positive integers where m is greater than n, we can put a equal to m squared minus n squared, b equal to 2mn, c equal to m squared plus n squared, and if those conditions are obeyed, then ABC will form a Pythagorean triple, or a set of three numbers which form sides of a right angle triangle. And I've got a quick proof that this formula works down here. Okay, so Simon introduced this on his video. I'm now trying to work alongside that. I don't wish to be competing in any way. But he asked the question on his video, which Pythagorean triples can be generated by Euclid's formula? So I've said these numbers will always generate a Pythagorean triple, but I'm not sure if every possible value of A, B and C, which form a right angle triangle, can be generated by numbers m and n in this way. Okay, so let's have a look now at some simple examples of Pythagorean triples. And I'm going to talk to you first of all about primitive ones in particular. So hopefully we've all heard of a 3, 4, 5. 3 squared plus 4 squared equals 5 squared. That's the smallest Pythagorean triple. There are some others that aren't too big. So the 5, 12, 13, the 8, 15, 17, and the 7, 24, 25. These are all called primitive because they don't contain any common factors greater than 1. I could scale these up, so in each of these columns I've scaled up by a factor of 2, by a factor of 3, and by a factor of 4. So 2 times 3, 2 times 4, 2 times 5. I'll look at the 8, 15, 17 next, multiplied by 3. So 3 times 8, 3 times 15, 3 times 17, 51. And I'll randomly choose this bottom right-hand one for the 7, 24, 25. If I multiply by 4, I get 28, 96, and 100 respectively. So these are non-primitive. So a primitive Pythagorean triple is one where the three sides do not have a common factor greater than 1. What I'm also saying is that in a primitive Pythagorean triple, not even two sides can have a common factor. So I've said that here. No two sides can have a common factor greater than 1. I put a short proof here. If two sides were to have a common factor greater than 1, then so does the third. And then we have a non-primitive which can be cancelled down by the factor r in this case. So a non-primitive Pythagorean triple can always be scaled down to a primitive 1. I could start with this 24, 45, 51, divide by 3, that's 8, 15, 17, for example. Okay, so let's jump into some serious business. I don't claim any credit for the next page myself. I found the proof on Wikipedia, So I'm going to show you that any primitive Pythagorean triple can be generated using Euclid's formula. I'm going to walk you through this proof. Please pause the video if I'm going a bit fast. Go forwards, back, watch it again. I'm going to consider a primitive Pythagorean triple ABC. We can only have one even side. We can't have two sides with a common factor 2, so we can only have one even side. So one of the two shorter sides has to be odd. I'm going to nominate this one as A. I'm not saying whether B is odd or even at the moment, I'm just saying that A is odd. If A squared plus B squared is C squared, then B is the difference of the squares of the other two sides. This is the difference of two square factorisation, so C squared minus A squared is C minus A times C plus A. B squared equals that, and I can rearrange this. If I divide by C plus A and divide each side also by B, I get B over C plus A equals C minus A over B. So what I'd like to say here, C is the longest side of the triangle. A makes it even bigger, so B is less than C plus A. So these fractions are less than 1. I'm going to put this fraction equal to n over m. N and m are both positive integers, and I'd like the fraction n over m in its lowest terms. So there's a unique possibility of what n and m can be. They don't have any common factors. If we were unfortunate enough to come up with a version with common factors, we just divide, we cancel the fraction until they no longer have it. So C minus A over B is n over m, and I'll turn this one upside down, so C plus A over B is m over n. So we've got some simultaneous equations to solve. If I add the two together, the 2c over b is n over m plus m over n, denominator mn, and on the numerator we get m squared plus n squared, and I halve it to get c over b in terms of m and n. What I do next is similar for the a's. I find the difference, so this one minus this one is 2a over b, so m over n minus n over m squared minus n squared over mn, and divide through by 2. We've got a similar expression, just with a negative sign there, for a over b. So if I can show now that I cannot cancel this fraction or this fraction in any way, then we're there. So because a and b have no common factors, if m squared minus n squared with 2mn have no common factors, and likewise m squared plus n squared over 2mn cannot be cancelled, then we know that we got the same numerator and the same denominator in each case. So it remains to show that these two fractions are in their lowest terms and cannot be cancelled. So m and n are co-prime. They don't have any common factors greater than 1. They cannot both be even. If they were both odd, then the square of an odd number always has a remainder 1 when divided by 4. So if you think of 2r plus 1 all squared, you get 4r squared plus 4r plus 1. I've got two coefficients of 4 and a constant of 1. I'd have a remainder 1 when I divide that by 4. So I'd have both of these squares with a remainder 1 when divided by 4, and so 4 is a factor of the difference of m squared and n squared. So that means the numerator of this fraction is divisible by 4, the denominator, remember I said that m and n are both odd, so the denominator fraction only has a 2 to the power of 1, but the numerator has a 4, so it's got a 2 to the power of 2. So numerator has a higher power of 2 than the denominator. Now, since this was a over b, it would imply that a is an even number, but I said at the very beginning a is an odd number. So that's not possible. Therefore, of m and n, one must be odd and one must be even. M and n have opposite parities, so an even square is even, an odd square is odd, so these are both odd, m squared plus n squared and m squared minus n squared. And so I cannot cancel these by a factor of 2 with odd numerators in both cases. So now we're going to try and cancel by a larger prime number, an odd prime, which will be greater than 2. If I could cancel either of these fractions, the prime number has to be either a factor of m or n. If it's a factor of one of them, so this is totally symmetrical now, if p is a factor of m, then it's got to be a factor of the square of m. Now bear in mind that we claim that the top is divisible by p as well. So if p is a factor of this, p must also be a factor of n squared. And if I take the square root, the prime number p must also be a factor of that. So if p divides n squared, p divides n. N basically consists of prime numbers, n squared consists of prime numbers all raised to an even power. So when I take the square root, I'm halving the power. The prime number is still a factor of n. So p is therefore a common factor of both m and n, and that contradicts what I said about m and n being coprime. So therefore we cannot cancel either of these by an odd prime factor, and so a over b and c over b are both in the lowest terms. We said at the start a over b and c over b are both in the lowest terms. We've just shown that the right hand side of the equation is also a fraction in lowest terms. So c equals m squared plus n squared, b is 2mn, and a is m squared minus n squared. That completes the proof. So once again, I've shown you there that any primitive Pythagorean triple can be generated by Euclid's formula. So the next thing is, what factors can we scale up by? Well, there are two kind of obvious answers here. If I increase m and n each by a factor of k, I increase a, b and c all by a factor of k squared. So I can scale up, certainly, any primitive Pythagorean triple by a factor of any square number I like, and regenerate it just by scaling up my m and n values each by a factor of k. The other thing I can do is double up. However, when we do this, the sides swap over. So my new triangle has capital M and N. My original smaller one has little m and n as its input values. The hypotenuse is always the same, the longest side of the triangle. But what was the scaled up 2 little m little n is now the difference of the squares of the capitals. And what was the difference of the squares previously is now the 2 capital M capital N when scaled up. But this basically gives me it's a two-way simultaneous equation, a two-dimensional simultaneous equation. but with 3 lines that have to be satisfied. If I add together my first 2 lines, 2 capital M squared is 2 little m squared plus 2 little n squared plus 4mn. Divide through by 2, we get this. So capital M squared is little m plus little n all squared. Since these are all positive, I can just take the positive square roots. So capital M is little m plus little n. And similarly, what I could have done, taken the difference between these, I would have had a negative 4mn there, a negative 2mn there, and got capital N is the square of little m minus little n. Capital N squared was the square of little m minus little n. And I come to this. I said as well, the third equation here is also satisfied, so a difference of 2 squares, mn will be m squared minus n squared, and I've got a 2 in front of it. That comes out in the wash. So there we go, we can scale up by a factor of 2 or a square number. In fact, we can repeat the process of scaling up by a factor of 2 as many times as we like. Once we've got something that's a Pythagorean triple represented by Euclid's formula, we can scale the 3 sides up by a factor of 2 again and again. So I can go by a factor of 2, by a factor of 4, by a factor of 8, by a factor of 16, by a factor of 32, etc. So a recap on what we know. Every primitive Pythagorean triple can be represented by Euclid's formula. That proof, again, I got off Wikipedia. I'll put a link to it in the video description below, so you can look that up for yourself if you like. Any Euclidean Pythagorean triple can be scaled up by a factor of 2 or any square number. So I've said I can scale up by a factor of 2 as many times as I like. Any square number, odd or even, but it's just the odd part that we're really bothered about because we can have as many factors of 2 here. I can combine the two, so I can basically scale up by any number, which is 2 to the power of r for some integer r times s squared for some integer s. For standard representation, I guess we can assert that s is odd and put all our 2's in the factor in here. But what we haven't discussed yet is what if we're scaling up by an odd factor which is not a square. So basically any factor for which we cannot scale up a Pythagorean triple and still use Euclid's formula, it will contain an odd prime factor with a maximum odd power, not a square. So we're going to discuss this on the next page. So any number which cannot be written in this way must have an odd prime factor p raised to a maximum power which is odd. So I'm going to call it 2l minus 1. That's my odd number. So scaling it by a factor of k, p to the power of 2l minus 1 is a factor of k, but p to the 2l, the next number up, is not a factor of k. So we got a Pythagorean triple scaled up by such a factor, and I've got my 2 sides, m squared minus n squared and m squared plus n squared. Now remember what I said earlier, in the primitive form, this number p could only be a factor of one or other of the sides. So therefore when we scaled up by a factor of p to the 2l minus 1, it can only be a factor, p to the 2l can only be a factor of one or other. So p to the 2l minus 1 is a factor of both this and this, but p to the power of 2l is a factor of at most one of those two, cannot be a factor of both of them. Right, so using the fact that p to the power of 2l minus 1 is a factor of each of those, I can add these together and it's still a factor, so 2m squared. I can find the difference, so this minus this. P to the 2l minus 1 is a factor of 2n squared. Since p is an odd prime, I can get rid of the 2, so p to the 2l minus 1 is therefore a factor of m squared and a factor of n squared. But since every prime factor of a square number must be raised to an even power, if I've got p to the 2l minus 1 as a factor, I must be able to go to the next step and say that p to the power of 2l is a factor, both the m squared and the n squared. So I can have the difference of these and the sum of these. I've got p to the power of 2l is a factor of both the difference and the sum, and I've contradicted what I said earlier on. So I've contradicted this sentence, this sentence, p to the 2l not being a factor of both of those. Right, so just time for the conclusion. In conclusion to this, every primitive Pythagorean triple can be generated by Euclid's formula. Every primitive Pythagorean triple scaled up by a factor, which can be written in the form 2 to the r times s squared for any integers r and s, can be generated by Euclid's formula. It is not possible to use Euclid's formula to generate a Pythagorean triple whose side's highest common odd factor is not a square number. So in other words, we can only scale up by odd squares if the maximum power of p is an odd power in the scaling factor, then we cannot do it. But we can, of course, if the maximum isn't even, because it means it's all square numbers that we're dealing with. Okay, well, thank you very much for watching. So once again, this has been a recap on which triangles can be generated using Euclid's formula. What I would like to do sometime fairly soon is put together a video on the corollaries of this, corollaries of Euclid's formula and Pythagorean triples. And I'll tell you now, there are some very interesting ones. So I think this video has been full of some, well, fairly intense proofs. I think the conclusion of this video is very interesting and useful, even if the proofs did get a bit involved at times. But thank you very much for watching. If you enjoyed it, please click the like button, and I will see you on my next video.